Triangle ABC has incircle omega, and there does not exist a point P other than A on the circumcircle with radius 4, such that the 9-point circle of triangle BPC is internally tangent to omega. The 9-point circle of a triangle is the circle that passes through the midpoints of its three sides. Given that AB plus AC equals 11, then cosine B minus C equals m over n for relatively prime positive integers m and n. What is m plus n? So this is the locus problem, and we're obviously going to have to track the locus of all possible 9-point circles of triangle BPC as P moves around the circumcircle of ABC. So let's just place P at some random point here and draw in triangle BPC. This is triangle BPC, and its 9-point circle is going to be the circle that passes through the midpoints of its three sides. The midpoint of BP, the midpoint of CP is here, and the midpoint M of BC is here. The circumradius of this triangle is obviously equal to half the circumradius of ABC, because the sides of this triangle are half the sides of BPC. So its circumradius is going to be half the circumradius of BPC. And the circumradius of BPC is always 4, no matter where point P is located, because it and triangle ABC have the same circumcircle, which has radius 4. So this 9-point circle is always going to have radius equal to half of 4, which is 2. But not only that, it's always going to pass through M, because that is the midpoint of side BC, which is common to all triangles BPC. They always have BC as a side. So it's going to have radius 2 and pass through M. If it has radius 2 and passes through M, then its center is always going to be located 2 units away from M. So the locus of all possible 9-point centers of triangle BPC is the circle centered at M with radius 2. So let's draw in that circle, which has center M and radius 2. This is the circle with center M and radius 2. Now what else? We have that the 9-point circle of triangle BPC is internally tangent to omega. So what needs to be true about the two circles? Well, if two circles are internally tangent, then the distance between their centers is this distance here. And that's exactly equal to the difference between their radii. So two circles can only be internally tangent if the distance between their centers is the difference of their radii. So the center of that 9-point circle of triangle BPC, it needs to be exactly the difference of its radius, which in terms of the circumradius is big R over 2, and the radius of the incircle, which is little r. If the 9-point circle and incircle are internally tangent, then the distance between their centers is big R over 2 minus little r. That's the difference of their radii. And we want the circle centered at I, the incenter, with that radius, big R over 2 minus little r. That's the locus of all possible points the 9-point circle could be centered at in order for it to be internally tangent with the incircle. And if there's only one point that produces this internal tangency, then those two loci can only intersect once. Only once. Because if they intersect twice, then there'd be 2 points that satisfy all the conditions required for the two circles to be internally tangent. We don't want that. We only want 1 point, A. So these two circles, these two loci only intersect once. In other words, they're externally tangent. The loci are externally tangent. And the distance from this center I to M is the sum of their radii. The radius of the circle centered at M is 2, which in terms of the circumradius and inradius is big R over 2. The radius of the circle centered at I, it's the difference of the radii of the 9-point circle and the incircle. So big R over 2 minus little r. So we can write that the distance between M and I is equal to big R minus little r, because that's their sum. Mi equals big R minus little r. Now the obvious thing to do would be to drop the perpendicular from I. It has length little r. And since Mi is equal to big R minus little r, let's call this point D, where the incircle is tangent to BC. We can find dm in terms of big R and little r. It's the square root of mi squared minus id squared. That's the square root of big R minus little r squared minus little r squared. The square root of r squared minus 2 big R little r plus little r squared minus little r squared. The little r squareds cancel out. this is just the square root of r squared minus 2r little r, which is the square root of big R times r minus 2 little r. So dm squared is equal to big R times big R minus 2 little r. But guess what? That's also equal to OI squared. This is exactly Euler's formula for the distance squared between the incenter and the circumcenter. That's OI squared. So dm squared equals OI squared. Now we can add in point O. Point O is right there. We have both OM and ID are perpendicular to BC, and OI equals DM. So in particular, OIDM is a rectangle. So it only makes sense to consider now the other pair of equal sides in this rectangle, ID and OM. Let's remove all these lengths we found earlier. They are not relevant anymore. Oops. So ID equals OM. Now, what's OM equal to? Well, if you draw in right triangle OMC, you see that OC is equal to big R. And angle COM is just half angle COB. But half angle COB is just angle A. So this angle here is angle A. And OM can be represented as R cosine A. Let's use a different color now. We have that little r, which is equal to ID, is also equal to big R times cosine A. So what's cosine A equal to? That's equal to little r over big R. But this little r over big R, that should remind you of the Carnot theorem, which we used at the end of 2016 USUMO problem 5. It's a previous video on my YouTube channel. You should go check it out. I'm pretty sure I used the Carnot theorem at the end of the YouTube video, which states that cosine A plus cosine B plus cosine C equals 1 plus r over r. Let's write that down. Cosine A plus cosine B plus cosine C equals 1 plus little r over big R. But cosine A is literally r over r. So cosine B plus cosine C is equal to 1. Now, what do we want? We want cosine B minus C. So what's cosine B minus C? Well, cosine B minus C is just equal to cosine B cosine C plus sine B sine C. So we clearly need something to do with the sines of angles B and C. But we are given that AB plus AC equals 11 in the problem statement. If you use the extended law of sines, you get that AB is equal to 2R sine C. This is true in any triangle. AB is equal to 2R sine C and AC is 2R sine B. So if you add them up, AB plus AC is just 2R times sine B plus sine C. And 2R is 8. So we have sine B plus sine C is equal to 11 over 8. Sine B plus sine C equals 11 over 8. Now this cosine B cosine C and sine B sine C, they look a lot like what you would get if you squared these two equations. They give you a 2 cosine B cosine C and 2 sine B sine C somewhere if you squared both of these. So let's do that. If you square this, you get cosine squared B plus 2 cosine B cosine C. Now you can see what we want forming. Plus cosine squared C is equal to 1 squared, and that's 1. From here, we have sine squared B plus 2 sine B sine C plus sine squared C is equal to 11 over 8 squared, and that's 121 over 64. If you add these, you see that cosine squared B plus sine squared B, that's just equal to 1. This is also equal to 1. And all that remains is 2 cosine B minus C. The sum of all of these is equal to 185 over 64. So 2 cosine B minus C is equal to 185 over 64 minus 2. That's 185 minus 128 over 64. That's 57 over 64. So cosine B minus C is equal to 57 over 128. Let's go back to the problem statement. It equals m over n for relatively prime positive integers m and n. M equals 57 and n equals 128. What is m plus n? It is 185. And we are done with mock AIME problem number 15. Thank you for watching this YouTube video. Please follow my channel and please get us to 375 followers before AIME 1 on February 1.